Hello everyone. Today's topic of presentation is about the stator frequency control method of induction motor. So various methods are adopted to control the induction motor. Among that is this stator frequency control method is one. And here we'll see that advantage and disadvantage associated with the stator frequency control method after this topic. So let me explain for first thing how to control the induction motor. What are the relations we have holding the induction motor by this frequency. Let me see the equation here. It is given as ns equals to 120 F by P. From this we can conclude that the supply frequency is directly proportional to the synchronous speed of the induction motor. Similarly, we can say that the speed, rotor speed, is also proportional to the frequency. Then another equation we can find here, it is supply induced voltage in the stator of the induction motor. We are saying it is as E1 induced voltage. Here for my convenience I represented here as V1. That equals to 4.44 times of frequency multiplied by the flux multiplied by turns, number of turns, and multiplied by the winding factor. So if you look at this equation, all the parameters except frequency and voltage, flux, these three remaining all are constant quantities except these three. Now I can say that here I am not concentrating on voltage control, so that I am also assuming that this induced voltage is also a constant quantity. Then what are the variable quantities again in the sense? Only the two quantities, remaining two quantities, flux and the frequency, these two. And how these are holding the relation in the sense, if you brought this flux to this side, because this voltage is constant and it seems that frequency is inversely proportional to the flux from this relation. Keep remember, frequency is inversely proportional to the flux here and the speed is directly proportional to the frequency here. These two relations is important. Now, how we can control the induction motor in the sense, in two ways we can operate by regulating the frequency. One is low frequency operation and another one is the high frequency operation as is described here. So how it is categorized by this low frequency, high frequency in the sense, this is based on the base frequency that is called as rated frequency of the supply. So as we know that the rated frequency is 50 Hz. Below 50 Hz frequency is also said as low frequency operation, and above rated frequency is said as high frequency operation. In both the cases, the voltage is assumed as constant. You can look at here, the voltage is constant. So now let us go first thing for low frequency operation at constant voltage. What happens? So by that induced voltage expression, as we have seen in the previous slide, that shows that by keeping voltage is constant. For the low frequency operation, what I am doing is I am reducing the frequency to the below the rated frequency, so that once the frequency is reduced, then what about the flux? We know the relation, already we discussed. We know the relation. Frequency is inversely proportional to the flux. If frequency is decreased, flux turns to increase. Once the flux is increased, what happened to the machine? What are the changes adopted in the machine? That we'll have to observe. The first thing that will be happen, that it will cause more magnetizing current. Magnetizing current in the sense, it is the field current to the induction motor. You already know that relation also. The field current or magnetizing current is proportional to the flux. Once the flux is increased, magnetizing current run by the induction motor is also increased. So then once the magnetizing current drawn by the induction motor is increased, this is drawing supply current from the input, so that line input current also increased. As in the same case, the line current and line voltage are get mostly distorted. The distorted type of waveforms you can observe in the line current and voltage waveforms. And so here also one more thing will be happen in the induction motor, that is increased core losses. As the magnetizing current becomes more, automatically the core losses are increased. And I am also saying that the line input current is also increased due to drawing more magnetizing current in the field winding. This obviously draws current from the supply, so that supply current also increased, so that the supply current is input current to the stator copper loss is also increased. So now the stator copper loss is also increased along with the core losses. So now as these two losses are increased, obviously the efficiency of the machine is falls down, hence it's a low frequency operation gives a very low efficiency. It is also due to the distorted waveforms and increased losses. The machine will produce high pitch acoustic noise. This unwanted noise will be produced in the machine, which is undesirable. So these are the drawbacks which are associated in the low frequency operation. Hence, we are moving for the high frequency operation. So here, if you see that the same relation holds to describe this high frequency operation also at a constant voltage. And I said again here voltage V1 is constant, and for high frequency operation I'm increasing the frequency of the induction motor above the base frequency, above the rated frequency, so that it is increased. Already we know the equation again. Can recall the equation. Flux is inversely proportional to the frequency. Once the frequency is increased, flux decreases. Once the flux is decreased, the rotating magnetic field strength also decreases in the air gap of the induction motor. Once the rotating magnetic field strength is decreased, the torque required to run the rotor is also reduced. So that is described here in this case, as we know that the speed is directly proportional to the frequency of the induction motor. Once the frequency rises, the no load speed of the induction motor is increases. These two are proportional, hence no load speed is increased. But if you look at the torque is depending upon the rotating magnetic field strength. If you have a less flux in the stator, the rotating magnetic field strength also reduced, and the torque produced also reduced. Both the type of torques, like maximum torque decreases and the starting torque also gets decreases. And this is also saying that the starting current also gets decreases. How the starting current is relating with this frequency, in the sense it is not directly related to the frequency, it is relating to the flux. Flux is proportional to the field current. Field current is a magnetizing current. Magnetizing current is a function of input current. That is what starting current. The starting current also decreases. So now these are the drawbacks which are associated with the high frequency operation at constant voltage. By looking this two, we can say that both the operations like low frequency and high frequency is having some drawbacks in this. Obviously, whenever the operation is required for the frequency control, then we'll go for this operation. Otherwise, we'll not follow this type of control. So here it is not the situation to give the conclusion. Let's move to the discussion. Now, once the frequency quantity is varied, either it is low frequency or high frequency operation, it is set based on a base frequency. That base frequency always we are termed as a rated frequency of the induction motor. So now One term I am defining here, this term is also called as frequency, denoted as K. This frequency is per unit frequency. This K is termed as per unit frequency. This per unit frequency is defined as it is the ratio of actual operating frequency to the rated frequency of the induction motor. Similarly, we can write the operating speed in omega s and the base speed of the induction motor in omega b. Actually, this base speed defines the rated speed, and this omega s now defines here in the case that operating speed and radians per second. So here how we are writing this omega s by omega b as f by f rated in the sense, you can write it is 2 pi ns by 60. Here is also 2 pi ns by 60. And ns is 120 f by p. Here also 1 ns equals to 120 f by p. So means that 120 by p, 120 by p gets cancelled. Obviously we'll be getting f by f. But this f is different from this. If f is equal to f rated, then you can get k is equal to 1. That we are saying at base operating frequency. The operating frequency of the induction motor is equal to rated frequency. Operating frequency is this one, rated frequency is this one. So then this is called as the rated operation of the induction motor when these two are equal. If it is less than the rated frequency, that is called as low frequency operation. If this f is greater than the rated frequency, then we are saying it is as high frequency operation. So that here we can able to define now the slip values like this. S is equals to, you know, that ns minus nr divided by ns. Here I'm writing omega s minus omega m. This is the synchronous speed. This is a mechanical speed. This is also synchronous speed. Like that I'm writing. And this omega s from this equation, from this omega s is equal to, I can write k into omega b. So that I'm writing k into omega b minus omega m divided by k into omega b. That equals now, by separating this ratios, we have k into omega b by k into omega b is 1 minus omega m divided by k into omega b. This equation will come. Now, let us write this in the torque equation. Before writing this, just write the general torque equation for rated voltage and rated frequency. Keep remember rated voltage, rated frequency. I'm not applying variable frequency here. Just for rated voltage, rated frequency, general torque equation I'm writing T equals to 3 by omega s V square divided by Rs plus Rr dash by S whole square plus Xs plus Xr dash whole square into Rr dash by S. This is general torque expression. Now I am going to writing for the torque equation of stator frequency control. Once if I go for the stator frequency control, what modification I am doing is I am replacing all omega s here with k into omega b, and the slip values, if I find some slip values, that also I'll write the function of like 1 minus omega m by k into omega b, and that modification I'll do. And here also it is also function xs and xr dash. These also function of a frequency. Xs we are writing as xs is nothing but it is the reactance function of frequency, and xr is also, this is also a reactance, we are also writing here it's a function of frequency. So that which one is affected in the sense this xs and xr dash will affected and this omega s is affected. That effect I am writing as T is equals to 3 by k into omega b into v square divided by, these terms will not be affected, and it's a function of frequency is now this one k into xs I'm writing plus k into xr dash whole square. So in general we are writing like this. So here I'm writing one statement that the frequency is above rated frequency, is that high frequency. Rs can be neglected as compared to the stator and rotor reactances. So actually what happening here is, so if it is high frequency operation in the sense high frequency operation in the sense this frequency is greater than this frequency, so that k is greater than 1, so that because the numerator is higher than the denominator, k is greater than 1. So k is greater than 1 in the sense, obviously previously it is xs plus xr dash, here xs plus xr dash. Now here it becomes due to effect of variable frequency, then here it is termed as k into xs. This k greater than 1 is multiplied with this, and plus k greater than 1, which is greater than 1 is multiplied with this, and these two are added and it is squared. As compared to this term is neglected. This rs is neglected first, and later I will see the operation, right? So as that is what here it is read. rs can be neglected as compared to the stator and rotor reactances, so that the torque equation becomes like this. The torque equation becomes now like this. So this is I'm writing here, and r dash is given after this v square. So the remaining equation resembles the same except this rs. Now again I can write one more expression, that the slip at which maximum torque occurs. So actually this slip at which maximum torque occurs, you know the formula, Sm is equals to r dash divided by under square root of rs square plus xs plus xr dash whole square. Here I am modified that Sm value because I neglected the rs value here, so that rr dash divided by under square root of rs square plus xs plus xr dash. Rs square is 0, it's neglected. So under square root of xs plus xr dash whole square and root is cancelled. And what we have is rr dash divided by xs plus xr dash. But here I am writing slip at which maximum torque occurs for variable frequency, so that it is multiplied by k for both. K into xs plus k into xr dash. K is get common. Yeah, that is a remain expression becomes like xs plus xr dash. And the next thing is I'm writing the maximum torque expression. So this maximum torque will come whenever you substitute a maximum slip value in the torque expression, right? So this slip is corresponds to the variable frequency operation. This torque is also corresponds to the variable frequency operation. If I substitute this S value as Sm, then this becomes maximum torque. So that the value of slip, this slip value, I am now substituting in this place, so that this becomes maximum. So now the slip value is replaced in the previous equation 2. So sorry, this one in this equation, so that becomes like this. So in place of s, I'm replacing this entire term, and again we have here another one more s. In that place, I substituted that, and the equation remains like this. And again, you modify and you simplify this equation. If you keep go like this, and we'll be getting one equation Tm. This is maximum torque, that equals to 3 by 2 omega b xs plus xr dash into v by k whole square. This is a simplification process. After that, we'll be getting this equation. If I substitute here k equals to 1, if I substitute here k equals to 1, then we can get the maximum torque at base speed. This is general maximum torque expression for variable frequency operation. The variable frequency quantity you can decide by the k value. Once the k is presented in the sense, that is variable frequency operation in your torque, right? So now I am taking k is equal to 1, f is equals to f rated. Once f is equal to f rated, your machine is operating at base speed. So you can say like that. So now I can able to write k is equal to 1 here. We can get maximum torque expression at base speed. Whenever this k equals to 1, that becomes maximum torque at base speed. That I'm writing TMB. by putting k value as 1 here, and that remaining expression will be having TMB is equal to 3 by 2 into omega b v square divided by xs plus etc. Same equation except k equals to 1 here by placing that. And now you see these two equations, and I can write now as the ratio of these two. Tm divided by Tmb, the maximum torque for variable frequency and the maximum torque at base frequency. So now I can write like these two, the ratio. And once I write the ratios, now what happened? This term, and cancel this term will be cancelled, this term will be cancelled, and v by k whole square divided by v square will be available, and again v square is also get cancelled, remaining 1 by k square is available, and that I am writing Tm by Tmb is equals to 1 by k square. So now 1 by k square, if I write if I cross multiplied by this one, then I'm writing a Tmb equals to maximum torque at base speed, or we can say that base frequency. Base speed, base frequency, both are common. Now Tmb I'm writing as Tm into k square. This Tm is nothing but the maximum torque for variable frequency, and these two now becomes a constant value because these two are equal now. So hence equal in the sense both are same value will be getting, it's a constant, because if I cross multiply this, it seems like a same. Tmb is equals to k square multiplied by Tm. What is the value of Tmb? Sometimes they'll ask the question. You can write now, if you know the maximum torque, if multiplied with the k as the per unit frequency value, multiply that and we'll be getting the value of Tmb. From the above equations, the maximum torque is inversely proportional to the frequency square, and Tm into beta square remains constant. It is not beta, actually it is, you can say that it is k. Sometimes it is written as beta, so you can also write it as a k, per unit frequency, you can talk. It remains constant. So now what we can say that once that you are assuming this is a constant factor, so from these two, this is a constant and I'm equating Tm k square is equals to constant. If I remove the equality, so that what happened, Tm is proportional to 1 by k square. So that relation will be maximum torque is proportional to the square of the per unit frequency. Per unit frequency, that we are saying. Here if your frequency will increase, the maximum torque will also decreases. That already we have seen. Maximum torque. If you increase the frequency here, what happening? If you increase the frequency here, the maximum torque is decreasing. That is showing by this equation. Similarly for the starting torque also, and the starting current also will be having the same. Here we can conclude that if you increase the frequency, the maximum torque will fall down. That is undesirable. And based on this relation, for different values of k, I am going to plotting a speed torque expressions. Here I am not directly relating with the speed, I am relating with the frequency. If I relate the frequency proportional to the speed of almost, will say that these are the speed torque expressions and this the speed torque characteristics. And now I can say that the different values of frequencies are considered. Let us say in this first curve is drawn for the rated operating frequency. F is equals to F rated. So that k value is 1. K is, now I am recalling that k is equals to F by F rated, right? If F is equals to F rated, k is 1. I am saying F is nothing but operating frequency, where the induction motor is operating. F rated in the sense rated operating frequency means that it is 50 Hz. You can say that if operating frequency is equals to rated frequency, you can say that k equals to 1. Now this is for the rated operating frequency. If I am going to increase in the frequency, then what happens? What change is observed here in the sense? Once I increase the frequency, I am going back again. If I increase this frequency, previously I am assuming these two are same, hence k is 1. Now if I am increasing this one, k is greater than 1, right? If I'm increasing this one and I'm keeping the same as this value, and k is greater than 1, I can get that I am treating that it is 1.5. And next to say, now once you increase the value of k, what happens to the maximum torque? Previously, for k is equals to 1, this is my maximum torque. If I increase the k value further, what shows this relation? If k is 1, we have one maximum torque. That is this one for k equals to 1. If k is increased to 1.5, if k is increased to 1.5, what about the maximum torque? This is increased and it is squared. Increased value is squared as 1 by k square, right? 1 by 1.5 whole square. Now what happened? Maximum torque is gets decreased. So now maximum torque is gets decreased for 1.5. This is another speed torque curve I am drawing. This is the induction motor speed torque curve only. But what change you need to show in the sense, you need to show that the maximum torque has fallen for k is equals to 1 to k is equals to 1.5. The curve's shape should be same. Curve shape should be same. Next is, if I take k is equals to 2, then what happens? Further, the same relation. If k is equals to 2 here, this is a 2 square, means 1 by 4. The maximum torque is further decreased. Again, maximum torque is further decreased. From here to here, the maximum torque has fallen. This is another curve. So then we can have different curves for different values of k. So along with the maximum torques, what are the decreased values you can observe from this curves? You can also observe the changes, the decrease in starting torque. Is it right or not? Here for first k is equals to 1, this is the starting torque. And if for k is equals to 1.5, this is again the starting torque is here falling down. You can see that for k is equals to 2. This is for k equals to 1.5. This is for k equals to starting torque further decreased compared to this. Again, if I increase the starting, this is the k value is 2.5, the starting torque is further comes down. And for 3, it further comes down. Means that the starting torque also comes down, falls down due to increase in the frequency, due to increase in the operating frequency. The changes we can observe in this speed torque expression and speed torque expression and characteristics. The expression is given here. Based on this only we plotted this, all these curves. This type of equation will be same equation. This I am returning one equation here. It is as Tm is directly proportional to k square. You can also derive the same expression for the starting torque. So similarly, starting torque expression also finally brought like this, and after that you can say that TST is directly proportional to 1 by k square. So based on that only this will be set. So for example, here one example is given. The rated frequency for motor is 50 Hz and TMB is 100 Newton meters. This is maximum torque at base speed. If the motor is now operated at 75 Hz, then they are saying what is the maximum torque. They are given one maximum torque value and one frequency. If it is suppose you are operating your machine at 75 Hz, then they are asking what is the maximum torque in the induction motor. So we need to equate that to this equation Tm k square, that is equals to TMB. So then from that you can get the value. TMB already they given as 100 Newton meters, and here you know that k square value, the k value is f by f rated. F is nothing but operating frequency where you are bringing the motor. It is 75 Hz greater than the 50 Hz. We are saying this is high frequency operation. Operating frequency is now 75, rated frequency is fixed, it is 50. Now the ratio of this is now 1.5. From this we can say that this per unit frequency is now 1.5. So now I substitute the values in this. TMB is 100, k square value is 1.5 whole square. what is the maximum torque? Maximum torque from this expression I'm deriving, so 44.44 Newton meters. From this we can conclude, from this example we can conclude, if a frequency is increased from 50 hertz to 75 hertz, the maximum torque is decreased from 100 Newton meters to 44 Newton meters. So from this we can conclude finally, due to increase in the frequency, the maximum torque, starting torque and starting current all or falls down. This is undesirable operation for the induction motor for the above frequency, above the rated frequency control also. So in some applications like blowers, fans, and some underwater installations, specifically they require the high frequency operation. There only we are following this high frequency operation, and for the remaining thing, this due to lot of disadvantages associated with this type of technique, we mostly you are not following or we are not suggesting this method of speed control for the induction motor. Hence, we are moving for another technique called as volts per H, volts per F, called as V by F control method, that we will see in the next class. Thank you.